Okay, good morning. It's time to start. So we have a 1 hour talk now. We have got Soheil and Alma. They're going to share the talk this morning. And yeah, 1 hour. Over to you, Soheil.
Everybody, today Alma and I are going to talk about matching sparsifiers, or I should say matching maybe simplifiers. And I will talk particularly about one application of these sparsifiers in the dynamic matching problem. And I also discuss their connections to Ruzsa-Szemerédi graphs and also a generalization that we call ordered Ruzsa-Szemerédi graphs. OK, so let me start with the mandatory slides. So what is a matching? A matching is just a set of vertex disjoint edges in the graph. So these red edges form a matching. And we'll be interested in a matching of large size, or maximum matching, which is basically the largest possible matching you can find in the graph. And this problem has numerous applications, from kidney exchange to image recognition, and so on and so forth. So today, we'll talk about sparsifiers for matchings. So in particular, I'll first talk about graph sparsification for matchings, and then talk about the application in fully dynamic graphs. So graph sparsification is an extremely strong tool in graph algorithms, as we all know, and we'll learn more about them this week. So they've been used extensively for cuts, or the cut sparsifiers have been used extensively for cuts. Spectral sparsifiers are used extensively. Spanners are some sort of a graph sparsifier. But now the question is, can sparsification be useful also for matchings? And indeed, they're also super useful for matchings, and we'll see how. So we'll first need to define what we really want from a sparsifier, because a matching itself is a very sparse subgraph. So a matching has only order n edges in it, so it's sparse. But what we want from a sparsifier is more than preserving just a maximum matching. In a similar way that we want cut sparsifiers to sort of cover all cuts in the graph, we want to sort of cover all matchings in the graph. And this was formalized in a very nice work of Goel, Kapralov, and Sanjeev from 2012. I'm going to refer to this paper a lot, so I'm going to call it GKK from now on. And this is a definition of what they called a matching cover of a graph, which is going to be the sparsifier we'll use for matching. So what is a matching cover, or in particular, what is an alpha matching cover? Think of alpha as a parameter between 0 and 1. So an alpha matching cover of a graph G is a sparse subgraph H of G. And by subgraph, I mean an edge subgraph. So we are picking a subset of the edges of the graph G. And we say the subgraph H is an alpha matching cover of graph G if the following holds for all choices of A and B. So A and B are vertex disjoint subsets of the vertices. And what we want from this matching cover is to cover the matching between A and B. So what we want is the matching size, the size of the maximum matching in the bipartite induced subgraph between A and B in subgraph H to be almost as large as the matching between A and B in the original graph. So I want to emphasize that we do not require the matching to be the same, to be using the same edges. So we could use different types of edges. So maybe like I'm missing all these 4 red edges in the matching sparsifier, in the matching cover, but I have 3 other edges that can be used to construct a large matching between A and B. And also, we're allowing an additive slack of alpha n. And this is the parameter alpha, which defines matching covers. So just to summarize again, a matching cover is a subgraph such that for every induced subgraph of the graph, it preserves the matchings up to an additive error of alpha n. And you may be wondering why we are allowing an additive error instead of, say, a multiplicative error of, say, half matching size G and A, a G of A and B. Well, it's not hard to see that if this was multiplicative, then we could just set A and B to be singleton vertices, and then we'd have to store whether that edge exists between them or not. So we cannot hope for sparse subgraphs if we define this multiplicatively. But if we allow the error to be additive, it turns out that matching covers could potentially be sparse and very useful. So yeah, so now the question is really, do sparse matching covers actually exist or not? Any questions about the definition of matching covers? Yeah.
So far, there's no constraint on basically the size of H. Like
yes. So yeah, so you can take H to be G itself, and it's going to be a perfect matching sparsifier with regards to the approximation, but it's not sparse. So we want the matching cover to be sparse as well.
Yeah. I mean, that's why do you enforce that is for every A and B?
Yeah. So we will see why. So similar to cut sparsifiers, why do you need all cuts to be preserved? Depending on the application that's going to be useful. Yeah.
So, I can see why it's a sparsifier. I just don't see why is it a cover. I mean, just the name.
Why it's?
Why is it covering? What is it?
called a cover and
Why is it called?
Like, you know,
Yeah, maybe Sanjeev should answer that because they called it.
You said it does not have to be the same edges. Like,
Yes, right. It's because there is the equivalent hitting set view of the problem, and so that suggested, that made us choose the name cover, and maybe so we will talk about the hitting set view.
All right. Okay. So, but do these matching covers? Do sparse matching covers exist or not? And first of all, for alpha equals 1. We can simply take the empty graph, and it's going to be the additive error is too large that we can just take the empty graph, and it's going to be a matching cover. So it's super sparse. But the more interesting case is when we set alpha to be half. And when alpha is half, so in particular, we can, if we take the matching to be, so if we take a subset A, B, and it has a perfect matching, and it's only if it only includes half of the vertices of the graph, the matching cover can completely ignore this matching. So it has an additive error of half the number of vertices. So long as the matching is smaller than half of the covers less than half of the vertices, the matching cover doesn't need to cover it. But it only needs to cover it if it includes more than half of the vertices. Okay. For alpha equals half, we do actually have really sparse matching covers. So in particular, in the original GKK paper, they showed that they gave a construction of a matching sparsifier, let's call it now, which they call the matching skeleton. Works for bipartite graphs, achieves alpha equals half with only order n edges. Okay. You can generalize this, or not generalize this directly, but you can achieve this almost the same bound of now half plus epsilon for general graphs, again with order n edges, using a different matching sparsifier called edge degree constraint subgraphs, or EDCS, which was introduced by Bernstein and Stein and has been used extensively since its introduction in 2015. So these matching sparsifiers are sparse. They preserve matchings that are not too small. And yeah, they've found a lot of applications. But now we may be, OK, so as we decrease the value of alpha, the matching cover covers more and more matching, smaller matching, which is what we really desire. So that question is, can we achieve sparse matching covers for alpha less than half? And the answer is that we actually don't know. We essentially don't know if sparse alpha matching covers exist or not for alpha less than half. But what we know is why we don't know that they exist or not. So we have a good reason to believe that this is a hard problem. And to explain that, I have to tell you what Ruzsa-Szemerédi graphs are, which is closely connected to matching covers. So what's a Ruzsa-Szemerédi graph? First, let me define induced matchings. So in a graph, we say a matching is an induced matching if there's no other edge in the induced subgraph of that matching other than the edges of the matching. So if you take, for example, this red matching, it's an induced matching because there's no other edge between the vertices of this matching other than the edges of the red matching itself. So this is an induced matching. And what's an RS graph, or Ruzsa-Szemerédi graph? So it has two parameters, R and T. R is the size of these matchings. So here we have a matching of size 3. And T is the number of these matchings. So an RT-RS graph is a graph whose edges can be decomposed into T edge disjoint induced matchings of size R. So here we have a 4-3-RS graph. So this is the first induced matching. This is the second induced matching. This is the third. And this is the fourth. So if you actually look at each one of these matching, it's an induced matching, importantly. There's no other edge inside any of these matchings other than the matching itself. And all of the edges of the graph are covered. Have I made a mistake so far? Yeah, OK, 3, 4, yeah. Yeah, thanks, yeah. OK, so we are interested in our RT-RS graphs for large R and large T. For R, we specifically want size of these matchings to be linear in the size of in the number of vertices. So we want the matching to match a constant fraction of the vertices. And now we want to make T as large as possible. So this is particularly the setting of RS graphs you're interested in for this talk. So intuitively, such RS graphs are locally sparse because if you take any one of these induced matchings, it's very sparse locally. There's no other edge inside. But if you look at them globally, it's a very global. It's a very dense. OK, at least if we can achieve high values of T, it's going to be a really dense graph globally. OK, so why are RS graphs connected to matching covers? So here's a simple observation. Take an RS graph, an alpha NT RS graph, and take one of its induced matchings. So suppose that this is one of its induced matchings of size alpha n. And now if we want to cover this graph, this whole graph, from this induced matching, suppose we want to cover, we want to achieve a matching cover with parameter 1 minus epsilon alpha, a little bit smaller than alpha. So now what we can do, if we take A and B, the subset of vertices, the matching between which we want to cover, to be the vertices of this induced matching, then we're going to have to include at least epsilon fraction of the edges of this matching in order to cover it. Okay. So then what this means is that if we want an alpha 1 minus epsilon alpha matching cover, we need to include a constant fraction of the edges of the RS graph, an alpha RS graph. So just to make this connection a little bit more clear, define MC n of alpha to be the smallest m, such that any n vertex graph has an alpha matching cover with at most m edges. So we want sparse matching covers. So let's take the smallest m for which these matching covers exist. And on the other hand, we want dense RS graphs. So define this RS to be largest T such that alpha and T RS graphs exist. OK, and I want to emphasize that here for MC, we're using the number of edges. Here we're counting the number of matchings, not the number of edges. So they're going to be a factor of n away from each other. But the trivial observation here is that basically, if you want to cover a graph with parameter alpha, we better use at least as many edges as the densest RS graph with parameter alpha, maybe a little bit more than alpha. And multiplied by n, because this is the number of matchings, we have to multiply it by the size of each matching. Yeah. So pick the largest T such that you can pack T many induced matchings in the graph. What do you mean? So this is the definition of RS. Yeah. Yes.
So the largest matching has size n over 2. Sorry, what?
Yeah. So
definitions were more like for n by n bipartite.
Okay.
yeah. So I wanted to I wanted to be consistent with the literature. So when it was first defined, it was for bipartite graph with n vertices on each side, so 2 n vertices in total. Yeah, I was hoping that nobody notices that, but yeah, but I was thinking, what's the simplest way to fix this? The simplest way is to when we talk about size of matchings, just count the number of vertices in it, not the number of edges. Okay, everything would make sense then, but yeah, it's a bit. You need to keep a constant fraction of its edges in the matching cover. So the matching cover should really have as many edges. Yes, exactly. Okay. So yeah, what this says is that if RS graphs can be too dense, matching sparsifiers don't exist. Matching covers need to be pretty much dense. So this is not too surprising. I mean, this is pretty straightforward. But the more surprising direction is the following, which was also proved by GKK. Basically, not only RS graphs lower bound the size of matching covers, they also upper bound. So the size of matching cover for parameter alpha is pretty much sandwiched between the density of RS graphs with parameter alpha, a little bit more than alpha and a little bit less than alpha. Okay. So what this means, in particular what the upper bound means, is that if RS graphs turn out to be sparse, we will actually have sparse matching covers. Or in other words, RS graphs are really the hardest types of graphs to cover. Okay. So, but what do we know about RS graphs? So RS graphs have been studied quite extensively for various applications, and people care a lot about them from various domains, but we don't actually know much about them. So from the lower bound side, a nice result of Fisher et al. From Stuck 2002 shows that the number of matching in an RS graph can be more than polylog n. This is n to the 1 plus 1 over log n. And for the upper bound, the triangle removal lemma of Fox from 2011 shows that the upper bound is n over log n iterated sum log of 1 over alpha times. So this might be a bit hard to parse, so let me simplify it a little bit. So the lower bound is n to the little o1. The upper bound is n to the 1 minus little o1. The trivial upper bound is n. The trivial lower bound is 1. So these are pretty much close to trivial bounds, although they're highly non-trivial, both the upper and lower bounds. Yes, yeah. It needs to be n to the 1. Sorry, yeah. That's the number of edges, not the number of matchings. Yeah, thanks. OK. So we could be living in two different worlds, depending on what the value of RS is. If the upper bound is close to be the right answer, if the upper bound is the right answer, matching covers must be dense. Matching covers are probably not that useful, at least when alpha is small. But in this case, we actually obtain many interesting lower bounds for various settings. Particularly in the streaming setting, we get a lot of lower bounds, not just for matchings, for a lot of other problems. We could also be living in a world where the lower bound is really the right bound. In this case, sparse matching covers do exist. But now the question is, can we actually construct them and use them efficiently? Okay. So this is particularly the world I'm interested in right now for this talk. So if the lower bound is the right answer, if RS graphs cannot be too dense, can we design fast algorithms or efficient algorithms depending on the resource that we are optimizing? So the question is, one concrete question is, can we find these matching covers that we know exist efficiently? And spoiler, we don't actually know how to construct them efficiently. So let me talk a little bit about constructing these matching covers. So this is the problem that still is open. So suppose that you're given a graph G, and you're given a parameter alpha, and the goal is to construct an alpha matching cover of this graph G with, at most, the density that we know matching covers exist for. Okay, so we know that every graph on n vertices has a matching cover with at most rs times n edges. But can we find such a matching cover efficiently, say in polynomial time? We do not know the answer to this question. And let me maybe overview one natural approach of trying to construct these matching covers and tell you why it doesn't quite work. So define the set of critical pairs C as follows. Take vertex subsets A, B, each of size alpha n, such that the induced bipartite graph between A and B has a perfect A-B matching. So take two subsets A and B that are that you can match them perfectly together, and both are of size alpha n. Now, to find a matching cover, it suffices to solve the following LP. You have a variable xe on every edge. Think of it as whether this edge is included in a matching cover or not. And what we want is for each one of these critical subsets, we want to include at least one edge. Okay. So it turns out that if we solve this LP and then random sample edges with probability xe times n, then you'd get a sparse enough matching cover. So it suffices to solve this LP. And this LP has only m variables, one variable for each edge. But the number of constraints is exponential. We have one constraint for every subset of vertices, which includes a large enough matching. Usually, this is not a problem if we can solve the separating oracle. Using the ellipsoid method, suppose that we are given some assignment to these x values, so long as we can verify whether all the constraints are satisfied or there is one constraint that's not satisfied, and we can point to that constraint, we can still solve such LPs in polynomial time. What's the separating oracle that we need to solve? Given x, find a critical pair AB that's not covered by x. The problem is, this problem actually is NP-hard. It's closely related to independent sets, so it's even really hard to approximate. OK, so we do not know how to solve this separating oracle. So we do not know how to get this to work and find optimal matching covers in polynomial time. Nonetheless, what I'll talk about is how we can sort of get around this and, at least in the dynamic setting, still construct matching covers efficiently. But before that, I want to actually mention this result we had with Sparsifiers and G and Juan in 23. So what we showed was that given any n-vertex graph, there is an algorithm running in n to the omega. Omega is the matrix multiplication power. So it's going to be n to the 2.3 time. That finds a really good matching cover, covers really small matchings containing little or one fraction of the vertices. The number of edges in the matching cover is at most n squared over some poly log star. So this doesn't directly relate to RS graphs, but still little o n squared. It still includes less than all the edges of the graph. So this led to improvements for long-standing, very slight but non-trivial improvements over long-standing bounds for matchings in dynamic and streaming graphs. And the reason that this bound appears is that we are using an algorithmic version of Szemeredi's regularity lemma. And the problem with this bound, though, is that the matching cover still needs n squared over log star many edges, even if RS graphs are too sparse. So that's why the previous problem still remains open. We really want matching covers that relate to RS graphs instead of regularity. OK. So now, for the remainder of the talk, I'm going to focus on one application of matching covers in the study of dynamic graphs. So in particular, we'll talk about the fully dynamic matching problem. Any questions so far? Yeah.
This may be a little unrelated. What if you assign weights to the edges in H, like in cut sparsification? Is that still impossible?
That's I don't know. That's a good question. Top of my head, I don't know if that helps. Yeah. OK, so what's the dynamic matching problem? Our goal is to maintain an approximate maximum matching of a graph that's subject to edge insertions and deletions, right? So maybe this is a graph, this is a maximum matching. Maybe this edge gets inserted, doesn't really change the maximum matching of this graph. But then maybe when this edge gets inserted, we can increase the size of matching. How? Maybe we can include these two and exclude this one from the matching. It increases the size of matching. Later on, maybe this edge gets deleted. Now we can include another edge. So we have to maintain an approximate maximum matching of the graph. And what we're optimizing is really the update time. So we're balancing the approximation ratio, what approximation of matching we are able to maintain, and how much time do we spend per update. So that's the main parameters that we want to optimize. There are other parameters, whether the algorithm achieves the update time bound in the worst case, or if it's amortized, whether the algorithm is randomized, deterministic, and so on and so forth. But today, I'll only focus on this trade-off between approximation and update time, not really caring about the other parameters. Okay. So this problem has been studied so very extensively. And it's very likely that I'm missing a lot of references here. So I actually want to skip this slide as fast as possible. But basically, if I want to summarize what we know in one slide, up until 4 years ago, this was the state of affairs. So for half approximations, we had really fast algorithms. This is actually really constant time even, but just to simplify this plot, I've written n to the little 1. So for half approximations, we can maintain matchings pretty fast. For 1 minus epsilon approximations, we had an algorithm by Gupta and Peng, which takes n time. N is the number of vertices per update. And there was also this algorithm in between, achieving 2/3 approximation in root and update time by Bernstein and Stein. This actually uses EDCS, which I mentioned is a matching cover for alpha equals half. So over time, there were other bounds in between. So with Sanjeev, we showed an algorithm which smoothly transitioned between these two bounds. And there are also a lot of works on algorithms maintaining the size as opposed to edges, and those algorithms can get significantly better bounds. I'm not going to talk about them. So what I'm going to talk specifically about is on 1 minus little o1 approximation. So we want to maintain arbitrarily good approximations of matching sizes, arbitrarily good approximations of the matchings, maintaining the edges of the matching. So using the matching cover that I mentioned, using the regularity lemma, we showed with Seper, Sanjeev, and Juan that there is an algorithm with update time a little bit less than n over some poly log star that maintains a 1 minus little o1 approximation of matching. This was improved this year by Yang to n over 2 to root log n. But what I want to talk about now is, again, when we are in a world where RS graphs cannot be too dense, question is, can we do better than this? And I'm going to talk about an algorithm we developed with Alma that has a running time somewhere in here. So the running time ranges from root n to close to n, depending on density of not RS graphs, but a generalization called ordered Ruzsa-Szemerédi graphs. And later, Seper, Sanjeev, and Peter improved the bound to this range, parameterized on the same quantity. Now their algorithm, if we are in the world where these ordered Ruzsa-Szemerédi graphs are sparse, the algorithm can take as fast as n to the little o1 time per update. OK. So let me tell you a connection between the dynamic matching problem and RS graphs first. And then using that, I'll motivate ordered Ruzsa-Szemerédi graphs and define them. So take an RS graph G. Suppose that we insert all the edges of this RS gadget in the graph. OK, so this is an RS gadget. We insert all of its edges one by one. And then here's this sequence of updates that the adversary feeds us. So the adversary goes over the matchings M1, induced matchings M1 through MT of the RS graph one by one. And whenever it reaches matching MI, what it does is it connects the complement nodes of MI to outside. So it takes these vertices not matched by, this is MI. It takes the vertices not matched by MI, connects them to outside. And then in this graph, you have to include all these edges in the maximum matching. And then the problem really is finding this induced matching mi. Okay. So then we delete these added edges. We move on to the next induced matching. We add the complement edges for that matching. This is the update sequence. This is not a hard instance, but it's sort of like an intuitively an input sequence that we do not know how to solve efficiently in a way that's natural and potentially can be generalized. So what this really tells us is that informally, RS of epsilon and update time is needed. But again, RS is the number of matchings in an RS graph. Why? Because whenever the adversary selects a new active induced subgraph, we don't know how to find this matching fast other than spending NT time, going over each verse, just a list of each vertex, and finding one out of the T edges that is in the matching, induced matching. So in total, we need NT squared time, NT time per each of the T matchings. And the total number of updates is just NT. NT to insert the graph, and N for each of the T matchings. Amortizing this is basically T, which is RS of epsilon n. So what this basically says is that we cannot hope to achieve update time better than RSN unless we have an efficient algorithm for this instance. Okay. And again, I'm not claiming that this is a hard instance, or I'm not claiming any lower bound. It's just an intuitive explanation of why RS dependency is needed. Now, an open question is, can we get better than, say, an update time if RS graphs are sparse? Actually, this still is open. We do not know. Even if RS graphs are sparse, we do not know better than an update time, polynomially better than an update time for dynamic matching. In other words, while RS graphs do capture a major challenge for dynamic matching, they do not actually capture all the challenge in a sense. And we need to parameterize our algorithm based on something that's sort of better tailored for dynamic matchings. And that's what ordered Ruzsa-Szemerédi graphs are for. So we define ordered Ruzsa-Szemerédi graphs as follows. This is a generalization of RS graphs, where each matching, instead of being induced in the whole graph, is only induced with respect to the previous matchings. So in other words, we have an ordering over the matchings. We have M1 through MT. The matchings come one after another. And each MI is induced in the graph that's the union of the first I matching. So it doesn't care about the matchings that come afterwards. So in other words, this is an example. So the red edges are M1. The green edges are M2. So if you look at M1, it's not an induced matching of the whole graph. There's this M2 edge matching two of the vertices of M1. But M1 should only care about the induced, to be an induced matching of the graph composed of just M1, which it is. On the other hand, when you look at M2, the induced subgraph of M2 is actually just M2 itself. There's this edge in M1, but the other endpoint is not matched in M2. So it is an induced matching in M1 union M2. So this is actually an ordered RS graph with two matchings of size 3. So every RS graph is an ORS graph, but the reverse is not necessarily true. So every RT RS graph is an RT ORS graph with the same parameters. And what this means is, in particular, remember, again, this should be n to the 1 over log n. Same here. So what we know is that RS graphs are sandwiched between n to the little o1 and n to the 1 minus little o1. So the lower bound applies to RS. Just take the RS construction. It's also an ORS graph. So ORS graphs should also can include as many as n to the 1 over log n matchings. But this upper bound doesn't quite apply because ORS graphs are more general. They're less constrained, so they can potentially be denser. And in particular, the way this upper bound is proved using the triangle removal lemma, as black box at least, doesn't apply to ORS. So by adapting techniques from a paper of Huang, Fox, and Sudakov, with Alma, we showed an upper bound that's qualitatively the same as this, but the dependence on alpha is worse. So it's n over log iterated, again, a constant number of times. But this constant has a worse dependence on this constant alpha. Here it was log. Here it's poly 1 over alpha. It's 1 over alpha cubed. OK, but morally, again, we do not really have a good understanding of density of ORS graphs. And now we want to parameterize the dynamic matching update time based on ORS graphs. So now let's go back to the hard instance. Now, let's slightly modify it. Whenever we pick this active induced matching and insert these edges outside, we don't just delete these edges outside for the next matching, but also remove this matching itself. OK. So this is the only modification I made to the update sequence. So I go over these induced matchings, these ordered induced matchings now one by one. And whenever I insert those edges outside, I also remove them afterwards and remove the induced matching together with them. So again, just go over this again. So this was the first matching. These are the edges outside. Then once I insert them, the algorithm has to find a constant fraction of these edges. And then I delete these edges along with the edges that go outside. Why do we delete these? Because we don't want the algorithm to be able to use them later on. We've revealed this matching, so let's not allow the algorithm to use them later on. And it turns out, with very much the same intuitive analysis, at least a naive algorithm on this graph takes now time proportional to ORS of epsilon n. And why is this useful? Because ORS could potentially be denser than RS, so this is a better lower bound. And now we can ask the same question. Can we get better than n update time if ORS is now sparse? And this one, we answered in the affirmative. That yes, if ORS is sparse, actually we can get around this n barrier. OK. So the result is the following. That there exists a fully dynamic algorithm that maintains a 1 minus epsilon approximation with update time, which is bounded by this. Roughly, it's root n times ORS. So if ORS is n to the literal 1, this is really essentially root n. If ORS is n, this is close to n. So depending on the value of ORS, we get an algorithm with different update times. This was later improved by Sepher, Sanjeev, and Peter to better dependency on ORS. So now this actually runs in n to the literal 1 if ORS is also n to the literal 1. And Sepher will talk about this. And he'll tell you much more about the algorithm than I'll get to. But let me tell you a little bit about some of the key insights behind the algorithm that I found interesting. OK, so the first tool we are going to use is a reduction to a version of the dynamic matching problem where we are given vertex queries. So to achieve an update time of t for the fully dynamic matching problem, it suffices to maintain a data structure such that upon any vertex subset query u, it can find an epsilon n additive approximate matching of g induced on u. Now, instead of t time, it can spend even t times n time. So instead of maintaining a matching at all times, the algorithm only has to report matchings of given vertex subsets and can spend n times more than the desired update time for each one of those queries. Intuitively, each one of these queries has size n, so we allow n times more to process those updates. So now to achieve a better than n update time, it suffices to find an approximate matching of GU, an additive approximate matching of GU in subquadratic time. It turns out that in a static setting, this problem is impossible. This is provably impossible. So if you're given a graph and you have natural query access to this graph, you need to spend n squared time to find any constant approximate matching of it. But what we show is that this can actually be done much faster in a dynamic graph, where we are given multiple choices of multiple such u's, and we have to, on average, solve each one of them fast. Okay, not for the worst case. So for some of them, you're spending n squared time, but intuitively, we're going to learn something about the underlying graph and not spend that much time later on. This is how we get around this barrier. OK, so I want to stop in 2 minutes. So I don't want to take too much time here. But some useful cases for why this is intuitively possible. So if GU is sort of d-regular, and think of d as larger than n to the epsilon, random sampling here finds this matching pretty fast. From every vertex, you random sample an edge. D of them are inside. The probability that you hit one of them is d over n. You repeat this n over d time, you will find one of these matching, one of these edges. Repeat this for all the n vertices in n squared over d time. You can find this matching. So if this is OK if d is large. Another extreme case is when GU is an induced matching. It's internally really sparse. Here, our algorithm is going to take too much time. It's going to take n squared time. So this is one of those bad choices of U. But whenever these bad cases happen, we charge the cost to ORS. Every such slow query reveals one induced matching of ORS. So there can be so many, so long as we remember them, so that we don't spend too much time on them again. And another case is when GU is empty. Random sampling still takes n squared time. It's still slow, but we don't have anything to charge to. So we don't really want to spend n squared time in this case. To avoid this, we use sublinear time matching size estimators. So we first verify whether there exists a large matching. And if there is not a large matching, we don't actually spend too much time. And this can actually luckily be done really fast. If you care only about the size of the matching, we can do this in order n time for say, a half approximation. This is a result I had back in 21. OK. So a few final remarks about the algorithm. And Sepher will tell you much more about how dependencies on ORS can be achieved. But a few things that I found interesting about this algorithm. First of all, we use the sublinear time matching size estimator for explicitly maintaining the edges of a matching. To my knowledge, this is the first application of these size estimators to actually find a matching. And it's crucial to estimate just the size when you want a sublinear time algorithm. And if you want to learn more about these sublinear time matching size estimators, do attend Mohammed's talk tomorrow. He'll tell you much more. And let's go back to the separating oracle I discussed. If you look at the separating oracle for this LP, we want to, given x, find a pair that's not covered by x. We don't know how to solve this separating oracle, but in this application, what we're doing is we're essentially relying on the adversary to solve this separating oracle for us. So the adversary is basically giving us this subset U. If we are covering it so far, great. If not, it tells us that it solves the separating oracle for us. So sort of like we're using the adversary actually in our advantage to solve the separating oracle problem. And finally, if the algorithm takes too much time, it can return a dense ORS graph. So if I care about even practical applications, I'd run this algorithm. If the algorithm is fast, I'd be happy. If the algorithm is slow, I solve a long-standing open problem in mathematics, and I'd be even happier. OK. Yeah, so I'm going to conclude here, and I'll let Alma tell you a little bit about upper bounds on ORS. And I'll just leave a few open problems here. Can we maintain 1 minus epsilon approximation strictly in less than n time, in polynomial less than n time, unconditionally? Can we prove conditional lower bounds for this problem? Can we upper bound the density of ORS as a function of RS? This is a problem Alma will also mention. And again, another question is, can we construct matching covers efficiently in static graphs?
Hey everyone, I'm very excited today to talk about upper bounds on ordered Ruzsa-Szemerédi graphs. The main part of my talk would be on the techniques that are used for upper bounds in RS graphs, and we will be trying to see how these techniques are capturing the similarities between these two types of graphs. So let's get in it. So I want to start with the main theorem that I will be proving. This is going to be given that we have a matching of linear size, an ORS graph that the matchings in this ORS graph is of linear size. We prove an upper bound of n over L iteration of log on n, where L is poly 1 over C. And this upper bound that holds here somehow motivates to ask this open problem that whether we can find a more direct relation between ORS graphs and RS graphs that would somehow directly give us intuition about whether the size of these two are the same or not. So this is a very interesting problem to look into. So now I'm going to start with the overview on the RS upper bounds that was mentioned by Fox, Huang, and Sudakov in 2015. So what they observe here about the RS graphs is this main insight that says if we have a matching, let's say here the red lines are the matching. Let's say VAWU is our matching. Now, if we pick a vertex from this matching and remove all of its neighbors from the graph, then we are only removing one another vertex from this matching. So this means that we're removing a lot of vertices. But this matching is not damaged at all. So this is because if VU was an edge here, then the problem that happens here is that this wouldn't be actually an induced graph. So this happens in RS graphs, but this is not true for the ORS graphs because we might have this early matchings that they have a lot of edges inside them that come from the late matchings after that appear along the way. So this is the problem that we are going to be solving throughout this talk as well. Now, the thing that we can use here is that we are given a matching. We pick one vertex here and remove all of its neighborhood from the graph. We are reducing the size of the graph with, let's say, a constant factor, but the size of this matching is almost the same. So this gives us an intuition to maybe try to use this observation in a way. The way that we are going to use this is that we want to find a lot of matchings that have the same high degree vertices. Let's say here U1, U3, and U5. Sorry about that. And then what happens is that we remove all of these vertices from the graph. We are reducing a lot of vertices, but the size of the many matchings that we found that share these vertices that we call pivots, their size wouldn't change at all. So this is the intuition that we have here. The way that we are going to use it is the following. So let's assume that we are given this RS graph here. Now, if we pick, let's say, W1 and U2 as our pivots that we are going to remove from the graph, then each matching, let's say the blue matching contains both of these W1 and U2, and the red matching does not contain any of those. So the thing that is important here is that we can classify this matching based on the set of the pivots that they contain. So if we pick, let's say, K high degree vertices as our pivots, and we partition the matchings based on which subset they contain, then we get 2 to the K classes, and we can classify our matchings into these 2 to the K classes, and there would exist a class that contains T over 2 to the K matchings. And now we have a class that contains a lot of matchings, but the pivots that they use is a fixed subset. So if we remove the pivots in this class, this would do the thing that we wanted. This would reduce the number of vertices and will only and that would only hurt the matchings a little bit. So this is what we want to establish here. The important thing that happens here is that when we are when we do this, then we can the number of so what I'm trying to say is that this would give us, when we are reducing the number of matchings, but the size of the matchings stay the same, this will give us an upper bound on the total number of, the upper bound on the number of the matchings. So let's get into how we can apply these methods to order Ruzsa-Szemeredi graphs. As I mentioned, if we have a matching that has appeared early on in our graph, let's say M1 here, then we have, it might, if we pick a vertex as V, it might have a lot of neighborhoods that are coming from the later on matchings. And this means that if we remove the vertex V and all of its neighborhood, this wouldn't help us. This would hurt this matching a lot because we might end up removing all of its vertices. So the thing that we are going to do is that if this was the opposite, if we have a late matching that, let's say M5 here, and we removed all of its all of the matchings that appeared earlier on, then this wouldn't hurt the size of this matching at all. Because if there was an edge, let's say VU, that came from a matching M1, then this matching M5 wouldn't be induced in M1. That is the definition of the ORS graph. So how we are going to make this more sense? I'm going to partition the vertices into two sets, early and late. The early ones are chosen from the first half, and the late ones are chosen from the second half. Now again, if I pick a matching from the late set, and then pick a vertex from this matching, remove all of its neighbors, then I'm not going to pick any other vertices from this matching. This is what going to give us the same intuition from the Ruzsa-Szemeredi graph. Okay, again here, this is a matching from a late set. I will be removing U1 and all of its neighborhood in the early set. And this gives me some intuition about how I can do this on the order Ruzsa-Szemeredi graphs. Now we need to find a lot of such matchings in the late set. So we need to find some high degree vertices, let's say U1, again, U1, U3, and U5. But I need them to have both high degree in the late set and also the early set. I need them to have a high degree in early set because I want to remove a lot of their neighborhood from the early set, and I also need them to have a lot of vertices in the late set because I need a lot of matchings there to keep intact. This is another problem that we solve. The main intuition is that we iteratively remove the vertices that have low degree in one of these two sets. And we prove that because we are removing not many edges, then we're not damaging a lot of matching. So we can have be left with, let's say, constant fraction of the total matchings and be fine. So the last thing that we add to this proof is doing these steps iteratively that give us this upper bound that we have. So we are going to use the same technique using the classification to do the to the k classes of the matchings and reduce the number of vertices and keep many matching in the same size. But if we do this again and again, we will end up with some matchings that are large, but the size of the graph is very small until the point that we cannot do this any further. That would give us, by applying this, we actually get, and we can do this in poly C rounds, and we get an upper bound that we wanted to achieve. yeah, that's what I wanted to talk about. Thanks for listening.
Thanks, Soheil and Alma, and also thanks for being so perfectly on time. Any questions?
Yes, sure.
So was there like a local identity you can claim that you're saying this is what happens after you apply this procedure for poly C rounds? Is there something that you can say this is what happens after one round and this is what iterated to give this final bound?
So for one round, we get a constant. So we find constant, let's say, constant number of vertices, and then we remove those. But the size of the matching would drop to t over 2 to the k, where k is somehow log n. Should be less than log n. So I don't know if I answered it.
So I guess if you applied once, you get an upper bound of n squared over log n, so long as the matchings are really close to covering half of the vertices.
I see.
If you want the size of the matchings to be smaller and smaller, then you'd have to apply it more and more, and then the upper bound gets weaker and weaker.
So is there an LP for, so RS graph or dual LP of matching covers? Is there an LP formulation? RS graphs can be written as a packing and then figure out what is the covering LP, or RS graphs cannot be written in that form?
You're asking if there's a equivalent notion of matching covers for ORS?
I guess, yeah, but the start will be, can you write ORS as a packing LP pairs? And then take it to all to see what it is.
It's a good question. Yeah, I'm not sure if it. Yeah, not sure. We can chat about this sometimes. All interested question. Yeah.
So what do people believe about the RS-ORS, and where do they expect to be?
So I guess these RS graphs actually for different, okay, so if you don't care about matchings to be linear in number of vertices, if you're fine with the matching having n to the 1 minus little o1 edges, say maybe like n over 2 to root log n edges, then surprisingly dense RS graphs actually exist. So RS graphs with as large as pretty much n choose 2 edges, this is almost complete graph, missing some little o1 fraction of the edges. So RS graphs, even with that many edges, exist, so long as the matchings are small enough. For linear matchings, I don't really know what people believe. It seems hard to make progress on either the upper and lower bound.
Do you think they will be of the same size?
That's a good question. If I want to guess, yeah. This is being recorded, so I'm actually, I'll tell you what my guess is, but offline. But it seems that like a lot of these upper bounds do apply, so maybe they can't be too dense, but yeah.
And are there any implications for dynamic maximal matching, or is this framework of RS that's been developed?
So that part of the algorithm, when we are reducing to the vertex queries, there you're losing some epsilon and edges. So you're gonna have to figure that out first to get an exact maximal matching. But if you want an exact maximum matching, there are already conditional lower bounds that n update time is needed. N to 1 steps.
You said if RS is dense, there's be no lower bounds for many problems. What are, can you?
Yeah, so for example, you want to find a matching in the streaming setting in a single pass.
Other than matching?
MIS, Sepper gave a talk about MIS lower bounds that uses these Ruzsa-Szemerédi graphs. There are reachability type lower bounds also, I guess, based on RS graphs. Yeah, so there are a lot of other problems other than matchings. for which we do get lower bounds if our graphs are dense.
So you had said that the existence of ORS graphs is it's intuitively an impediment to dynamic matching. But is there anything more formal than that? Like, is it no?
Yeah. So we do not even have a. We do not have even a conditional. So there are a lot of fine grained complexity lower bounds for various dynamic problems. For matching, we do have lower bounds either if we want an exact maximum matching or if we want to make sure that the matching doesn't leave any short augmenting paths. So for these types of, so one way of achieving one subset approximation is to make sure that the matching doesn't leave any augmenting path of length less than 1/epsilon. If you want to ensure that there are fine grained complexity lower bounds, this algorithm doesn't guarantee this. And for just generally for obtaining 1-epsilon approximation, we do not even have conditional fine grained complexity lower bounds at all. Sort of this algorithm is explaining why we cannot have n lower bounds or large lower bounds, but even we do not even have, say, log n lower bound or the polylog n lower bounds. Yeah, that's a very interesting open question.
Any more questions? Good, then we have until 1/4, so we have quite a nice long break. Okay.